Now, the tricyclononane uranium center does not engage in electrochemistry, but the mesotyl derivative that I've just shown to you does. And at a redox potential of minus 2.5 volts versus the ferrocene-ferrocenium couple, you do actually see a redox wave that you don't see in the tricyclononane case. And so when you take potassium sand, or something later we take electrides, you can actually transform the trivalent uranium complex into a divalent uranium complex. You can actually monitor that by NMR spectroscopy. There are these very two features that are clearly observed in the uranium-3 species, and they shift to the low field side of the spectrum when upon reduction. The spectrum remains relatively simple, and so we were hoping that the uranium center would also keep its geometry. As I said, an improved synthesis goes via metal electrides, not via potassium sand. It gives you purer compound, it gives you higher yields, and from those solutions you will eventually get a molecular structure, and this is a molecular structure of a uranium-2 species, which at this time was a new oxidation state, but now we see a handful of these new uranium-2 oxidation states, and so we no longer have 6, 5, 4, 3, but also uranium-2 compounds. Now, this is the molecular structure, and in order to prove that it really is a new oxidation state, we compared the uranium-3 precursor with the uranium-2 reduced species. We overlaid this, and what we see here is, without going into great detail, is that the uranium-oxygen bond distances get longer, and the uranium-arene distance gets shorter because we now have increased delta backbonding. Most importantly, the CC bond distance do not change, and that means that we have a metal-centered reduction and not a ligand-centered reduction. Now, we did a lot of spectroscopy and magnetization, and I want to skip this part, only saying that if you do characterize a new oxidation state by spectromagnetochemical methods, it's really difficult to identify a new oxidation state if you have no comparison. And so eventually we had to compare our uranium data with plutonium data, because plutonium has a 5F4 electronic configuration, and when you plot the inverse susceptibility versus the temperature, these new data look suspiciously similar to the plutonium-4 data, and so we claim that our compound is the one electron reduced uranium-3, which is F3, to uranium-2, which now is F4. A computation also shows that we have these two HOMO-1 and HOMO-3 orbitals occupied. They have delta symmetry, and then we have two more metal-centered orbitals occupied with the two remaining electrons. Now, I should mention that there is another uranium-2 species, and that uranium-2 species does not have an F4 electron configuration, but a 5F3-61. And since I already mentioned that there are now a handful, in fact, to be precise, 4 different uranium-2 compounds, 2 of them have the F4 configuration, and 2 of them have the F3D1 electron configuration. Now, coming back to the delta bond, this is the bond that we wanted to see in electrocatalytic applications. And we do have the uranium-2-3 couple now, we have the 3-4 couple, we have the 4-5 couple. In fact, we also have the 5-6 couple now, but for some reason it's not showing here. And with that many oxidation states available, you should be able to accomplish this very simple reaction, the electrocatalytic reduction of water. And that's exactly what this molecule does. This uranium-3 molecule reacts with water to eliminate dihydrogen. This reaction is actually fairly unspectacular because uranium-3 reduces pretty much everything. I mean, you have seen that uranium-3 reduces CO2, and CO2 is an inert gas, right? So it's not surprising that uranium-3 would reduce water to eliminate the hydrogen. What is surprising is that this molecule is a relatively stable and insoluble molecule because the 3 elemental groups actually prevent it from dimerization. If you have less steric bulk, this molecule would actually dimerize, generate another half equivalent of dihydrogen, but then it would be the end of the story because you form a mu-oxo. But here we have this the species, we can isolate this, but we don't have to isolate it. Electrochemical reduction will generate the uranium-3 monoanion. Now with all these negatively charged ligands, this molecule is unstable and will eliminate hydroxide to actually regenerate the catalyst. So we have a catalytic cycle that combines chemical and electrochemical reaction steps to produce hydrogen. It's an EC mechanism, and we demonstrate that this is one of the first examples where we actually cleave a uranium-oxygen bond. This is not an easy task, and of course it is getting more difficult as you have formal double bonds and formal triple bonds. Now the electrocatalysis is shown here. Of course, a platinum electrode will reduce water at a lesser overpotential. Even a glassy carbon electrode will eventually reduce water, but our catalyst is right in between here. We could also show that simple trivalent uranium complexes would not do any electrocatalysis. Now the charge transfer resistance is shown here without a catalyst. You can see here we are looking at mega-ohm resistance, and when you add a catalyst, typically what you see is this Nyquist plot where there now is another half circle in between. We did not see this another half circle and were relatively surprised, but when you zoom in right here, you actually do see the half circle. And the reason you don't see it here is because the charge transfer resistance is reduced by 3 orders of magnitude. We go from mega-ohm to kilo-ohm here, so it's a fairly efficient catalyst. Now, when we wanted to publish this work, one of the reviewers was insisting that we should actually compare this first F-element-based catalyst to a transition metal catalyst. And comparing catalysts is actually exceedingly difficult. You need to compare catalysts and you need to compare performances under exactly the same conditions. So I contact a friend of mine, Dubois, who has the most prominent and the most performing nickel-based electrocatalyst. And he said, Karsten, I can send you that material, but it won't help you for your comparison because A, the nickel catalyst is not soluble in water, and B, it doesn't reduce water, it reduces protonated DMF. And so these two systems cannot be compared. Fortunately, Jeff Long and Chris Cheng at UC Berkeley, they had this system, and this is also a fairly competent catalyst for water reduction, and this molecule is soluble in water and it actually reduces water. And so we had to compare our catalyst with the molybdenum catalyst here shown in magenta. And what you see is probably here that our uranium catalyst starts to kick in at a lower overpotential, but then when the molybdenum catalyst kicks in, the molybdenum catalyst is considerably more active than the uranium catalyst is. Well, eventually the editor was convinced, and we now report that the catalyst lowered the overpotential by 0.5 volt. It increased the steady state electrolysis current by a factor of 10, and it lowered the Faraday resistance by 3 orders of magnitude. We were wondering, I mean, these two molecules look very similar, and we wondered why this one is an active catalyst and this one is no catalyst. And so is it the mesothelene anchor? Is it the delta buck bonding, or is it structural flexibility? maybe there's an additional coordination side. And so we looked a little bit at the mechanism and started with the stoichiometric reaction. Sure enough, this molecule reacts with water. It produces dihydrogen. It forms a hydroxide species, as can be seen nicely in the vibrational infrared spectrum. And the reaction is surprisingly clean. I mean, I should actually add a note. In uranium chemists, the most uranium chemists actually try to prevent water by all means, because molecules, uranium molecules, are so exceedingly sensitive towards water and oxygen that our students are drilled to actually work under water-free and air-free conditions. So if you actually add water on purpose, you are surprised to see that it's a relatively clean transformation. We also got a structure, and without going into great detail, this structure is one of the very few structures in which the compound is not trigonal symmetric, but it is actually 6-coordinate with this tetragonal plane, where now a THF binds in the equatorial plane. It opens up this trigonal plane to allow the fourth ligand to come in equatorially. So this seems to be super important.